welcome to the Exam 3 review problems. So here we'll be taking a look at just a couple of problems to help get you in that review mindset, try to recap some of the main topics that we discussed over the last few chapters. I highly encourage you to give these problems a try on your own before watching the video with the solutions. But then once you are done with that, try to follow along step by step and see how you're doing with this material. So to start off, we're given a differential equation. This is a non-homogeneous differential equation because we have these derivative factors on the left-hand side, and we have this function on the right-hand side. First, we need to find the complementary function yc, then the particular solution yp, but we will not solve for the constants in that particular solution, so that'll simplify our work a little bit. For the complementary solution, we're going to need to solve the corresponding homogeneous differential equation. So we're going to take d minus 4 d squared plus 12d plus 45 squared of y equals 0. And we need to convert this into the auxiliary equation. So that's going to be r minus 4 r squared plus 12r plus 45 squared equals 0. And we need to get the roots for this auxiliary equation. The first one, of course, r is 4. This second set of terms, however, is not factorable in that current form, so we need to use something like the quadratic formula. So we're going to get negative 12 plus or minus 12 squared is 144. Minus 4ac, so that's 4 times 1 times 45, so that's 180 all over 2a, so just 2. 144 minus 180 is negative 36, so negative 12 plus or minus rad negative 36 all over 2. That's going to give us a 6i, and then we'll go ahead and divide everything here by 2, so that gives us negative 6 plus or minus 3i. And be very careful, take note, the fact that this was squared means that any root produced by this has a multiplicity of 2. So we're actually going to have 5 roots here. We have the 4, and then we get a pair of roots for the complex, and there's 2 of each of those. So that gives us 5 roots total. So that's going to give us 5 terms in this complementary function, so yc of x. So we're going to get c1 e to the 4x. The complex give us the e to the ax cosine bx and e to the ax sine bx, that pair that come with the complex conjugates. So we're going to get e to the negative 6x cosine of 3x plus c3 e to the negative 6x sine of 3x. And again, if they didn't have a multiplicity of 2, that would be it, but each one of them occurs twice. So we're going to basically repeat these solutions, but with a factor of x in front of them. That's what happens when we have repeated roots. So we get c4x e to the negative 6x cosine 3x plus c5 x e to the negative 6x sine of 3x. And that will be our complementary solution, or our complementary function, where we solve the corresponding homogeneous differential equation. For part B, for the particular solution, we're trying to solve the non-homogeneous piece. So the non-homogeneous portion of this differential equation, we're finding one particular solution to it. So we need to determine the annihilators that we can use. In this case, this one does have proper form to use annihilators. So we're going to use annihilators. So a of d, let's see. So we're going to get, for e to the negative 5x, we get d plus 5 because it's d minus negative 5. For e to the 4x, that's d minus 4. For the cosine of 1x, that's going to be d squared plus 1. And for the plus 15, this one technically is counted as a polynomial, but it's to the 0th power. So that'll be d to the 0 plus 1, so just d. So just times d. So these are the annihilators that will be performed on this, the non-homogeneous portion of this differential equation, to essentially turn it into a homogeneous differential equation, right? That's how we solve these problems. If it's not 0, we're basically making it become 0. So what happens is we would apply this to both sides of the differential equation. On the left-hand side, it's going to give us more roots. On the right-hand side, it's going to turn it into a 0. So we end up getting, so we get new roots to the auxiliary equation. So we get negative 5, 4. This one will give us a 0. This one will give us a plus or minus I. So we got a few here. Now for the particular solution, we're going to go ahead and not use C1 through C5. We're going to use the capital constants, so A, B, C, D, E, etc. Because normally we would be solving for these by like taking the derivatives, plugging it back into the original differential equation, solving for all of them. But of course, we don't need to solve for them in this case. So negative 5 is going to give us, that's a e to the negative 5x plus, for the 4, be very careful. We already had a 4 as a root back in the original. So this is actually a repeated root. So this is going to be b times x, e to the 4x. Plus the 0 case, that'll be c e to the 0, so just c times 1. Plus d, this is, for these complex factors, e to the ax, cosine of bx, and sine of bx. A is 0 here, there is no term there, and then b is 1 in front of the I. So this is just going to be e to the 0, and then so that's just 1, cosine of 1x, plus e, so capital E, the constant, e to the 0, again, sine of x. And that is our particular solution for this non-homogeneous differential equation. And of course, the question didn't ask for the general solution. If it did, we would not have enough space on one line to write it all, but it would just be the complementary plus the particular. So you just add those two pieces together, and that produces the general solution. Let's go ahead and take a look at our second problem. Find the general solution to the linear system x prime equals ax, where a, our matrix of coefficients, is given here. So in order to solve this system, we're going to need to find the eigenvalues and eigenvectors that go with this matrix of coefficients. So we're going to take the determinant of 4 minus lambda, negative 1, 1, 2 minus lambda, set that equal to 0. And now solve that out. So we get 4 minus lambda times 2 minus lambda minus negative 1, so plus 1 equals 0. Expand that out. We get lambda squared minus 6 lambda plus 8 plus 1, so that's plus 9 is 0. Factor, this one does factor as lambda minus 3 squared, which gives us lambda equals 3 and 3, or you can just say 3 with a multiplicity of 2. So to get the corresponding eigenvector, we look at the null space of a minus 3i. So we subtract 3 off there, we get 1, negative 1, 1, negative 1, augmented with zeros, which, of course, very clearly that second row is going to get eliminated. So our eigenvector, we get the free variable here, we have the pivot here, so that's going to give us a 1, and then add that over, that gives us a 1 for the first component. So this will give us our first solution. So that gives us x1 of t is c1 e to the 3t times 1, 1. Now, unfortunately, this matrix is defective. We only had one eigenvalue. It produced one eigenvector, even though its multiplicity was 2. So we have a 2 by 2 matrix, an eigenvalue with a multiplicity of 2, but only one eigenvector. So we need to work with this one as defective. So we need to do a little bit of setup here. So since A is defective, we need x2 is going to be c2 e to the lambda t w1 plus tw2. This is that general form of our second solution, okay, where w1 will be chosen so that when multiplied by a minus 3i, it produces w2, which will be an eigenvector. And when multiplied by a minus 3i squared, it'll produce the 0 vector. So if we look at a minus 3i, that's just 1, negative 1, 1, negative 1. If we look at a minus 3i squared, so we take the matrix times itself, we get 1 minus 1, so 0. We get negative 1 plus 1, so 0. And then same thing, we get a 0, we get a 0. So this is good, because we need to choose w1 of t so that when it gets multiplied by this matrix, it produces w2, which will be an eigenvector, so it should be some multiple of this vector. And when it's multiplied by this one, it produces the 0 vector. And this one is the 0 matrix, so that makes our choice a lot easier and a lot more kind of free. So we'll go ahead and use 1, 0 for w1. So then a minus 3i times w1. This essentially just tells us to grab the first column, and that will be w2 of t, which needed to be an eigenvector, and it is. And in this case, it's not just an eigenvector. It actually is the same eigenvector. It's not even a different multiple of it, but that gives us w2 and a minus 3i squared times w1. Of course, the 0 matrix times anything will be that 0 vector there as required. So it does satisfy that condition. So these are proper choices for w1 and w2. So our second solution, x2 of t, that's going to be c2 e to the 3t times 1, 0 plus t times 1, 1. So we have x1, we have x2, and our general solution is just going to be the sum of both of those. So we get x of t is c1 e to the 3t times 1, 1, plus c2 e to the 3t times 1, 0, plus t times 1, 1. So that would be the general solution to this system of linear differential equations. And of course, you could combine these all and put them into like a vector form and just kind of consolidate everything. But we don't have to. It would be equivalent, but we can just leave it in this expanded form. But that brings us to the end of our quick couple of review problems for exam 3. Be sure to go back through, look at these solutions, look at your notes, look at that table of annihilators that we used for that first problem, these formulas, these processes for this second one. Good luck with the rest of your preparations for the upcoming exam. Let me know if you have any questions, and I will talk with you all very soon.